This is a short tutorial on the topic of solubility and precipitation reactions and how we write these reactions as molecular, ionic, or net ionic equations. Well, the question that we're trying to address here is why are some materials soluble in water or other solvents and other materials insoluble? Well, as I insist with every topic in general chemistry, energy is the reason for everything. In this case, the energy that we're looking at is a balance of three components. We're looking at the energy of interaction between individual solute molecules, the molecules we're trying to dissolve in our solvent, the energy of interaction between the individual solvent molecules, and then finally, the energy of interaction between the molecules of solute, what we're trying to dissolve, and the molecules of solvent, the liquid that we're trying to dissolve it in. From an energy point of view, what we find is if the energy of interaction between solvent and solute molecules is higher than the energy of interaction between solvent molecules plus the energy of interaction in solute molecules, the material will be soluble. If the energy of interaction in solvent solute molecules is less than the sum of the other two energy terms, then the material will be insoluble in the liquid that we're trying to dissolve it in. Well, if we take a look at reactions that produce a precipitate or a solid material after we mix two reagents together, we have a number of ways of writing those in balanced chemical equations. The first way we have of writing these balanced chemical equations is a molecular equation. In a molecular equation, typically we write something that looks like this. We're going to take one of our materials, barium chloride, and by putting aqueous in parentheses, we're indicating the material is soluble in aqueous solution, which means water. And we're going to add to that an aqueous solution of sodium sulfate. Again, by putting a parentheses AQ after that, we're indicating that sodium sulfate is in fact soluble. If we mix those two solutions together, we end up producing a barium sulfate in the solid phase, indicating that barium sulfate is insoluble in our water solution. And also produce sodium chloride, again with an AQ after that, indicating that sodium chloride in fact is soluble in water. Oftentimes, many of us will also emphasize the fact that we've produced a solid material which will precipitate out of solution by putting a little down arrow showing that that material comes out of solution. So that's the molecular balanced equation. We can also write what's referred to as a complete or full ionic equation. And instead of writing barium chloride as a, for instance, with an AQ after that, if barium chloride, an ionic compound, dissolves in water, that means what we have is in fact barium ions in solution, chloride ions in solution, no longer associated with each other. So the complete or full ionic equation is a better description than the molecular equation because we're acknowledging that barium chloride no longer exists as a compound, but as separated ions once we put it in water. And of course, we have the same situation with sodium ions and sulfate ions from our sodium sulfate. Then we show barium sulfate as a compound, solid compound precipitated out of solution, and then indicate that both our sodium ions and chloride ions remain dissolved in solution. Under these circumstances, we refer to sodium and chloride ions as spectator ions because they're not involved in the chemical reaction. They're spectator ions because they just stand around watching. And then finally, we have the net ionic equation, which is much simpler to write, and all of us are lazy, where we simply show the ions that are involved in the reaction of interest. In this case, we have barium ions dissolved in our aqueous phase. We have sulfate ions also dissolved in our aqueous solution, and the overall reaction produces barium sulfate, which is a solid and precipitates out of solution. What the net ionic equation tells us that we don't have to use barium chloride or sodium sulfate as long as we walk into the stockroom in our chemical laboratory and find a sodium salt of barium which is soluble, I'm sorry, a soluble salt of barium. And a soluble salt of sulfate. It doesn't matter what the spectator ions are, we'll get the same results. We'll have the same overall chemical reaction. Let's just practice that one more time with a different set of compounds. In this case, our molecular reaction will be calcium chloride and sodium carbonate, giving us calcium carbonate, which precipitates out. We're interested in this reaction because it produces limestone, which we see all over our environment. And of course, any aquatic organism which produces a shell is conducting this reaction to produce the shell. Following up with our complete or full ionic equation, we start out with calcium and chloride ions separated, dissolved in solution, sodium and carbonate ions separated, dissolved in solution. And our overall reaction then shows us that calcium carbonate precipitates out, that sodium and chloride ions stay in solution. And I see I have a mistake in this slide. It should be CO4 calcium carbonate. Again, sodium and chloride are spectator ions in this reaction. They're not involved in the reaction. So when we produce our net ionic equation, we simply have calcium ions in solution reacting with carbonate ions in solution to give us a solid sodium carbonate precipitating out as a solid. And again, we can use any soluble salt of calcium. We can use any soluble salt of carbonate that we can find in our stockroom and get the same results.